All right, so welcome everybody. Apologies for the hiccups of the technology and for the slight delay in the start. So thanks for sticking around nevertheless. A very warm welcome to our online attendees, and we're delighted to have Professor Arieh Iserles from Cambridge today here in Cardiff in person, and he'll be talking about orthogonal systems and stable spectral methods for time-dependent PDEs. So thank you very much for accepting our invitation and for being here, and straight over to you.
Thank you. And well, you have just seen the effect of too much technology and its influence on humanity, but at least ultimately it works. So let me explain very briefly the motivation underlying all this work. So suppose that we have a time-dependent PDE. L is a linear, for simplicity, a linear well-posed differential operator. It is given with some initial and boundary conditions. So let me explain briefly what are spectral methods. Suppose that we have a sufficiently smooth orthogonal system in L2. So being sufficiently smooth, it will live in some Sobolev space. And so here are conditions for orthonormality. A spectral method approximates the solution of the PDE by a truncated sum where the coefficients here are given by Galerkin conditions. So simply, you want the remainder to be orthogonal to all the elements of the basis. You use integration by parts as necessary, and this gives you a system of ordinary differential equations for the UMs, and you solve them by any standard numerical method. So what do we want from this orthogonal system? We want several things. One is stability. So the original operator is well posed. We want also the numerical discretization to be well posed. We want energy conservation. If it so happens that the exact solution conserves energy or conserves mass, like for example, say the Schrödinger equation or the wave equation, we want also the numerical solution to inherit this feature. And this, by the way, implies stability. We want fast convergence. So we have capital N coefficients, and we want everything to converge rapidly once we increase capital N. So we want this UN hats to tend to 0 rapidly once N is large. So in other words, the truncation depicts very well the exact solution. And this typically is the great advantage of spectral methods. They converge really fast. And finally, we want low cost. So we want to advance from K delta T to K plus 1 delta T in a small number of operations, ideally using devices like fast Fourier transform and so on to have cheap computations. So this is what we want. And let me now start going into the real presentation. So suppose that we have a complete orthonormal system, and suppose that our functions are at C infinity. Then there exists a natural map. Actually, it is enough that they're in C1, but I don't want to repeat it all the time, also when we need higher derivatives. There exists a natural map taking functions to their derivatives. Given that the derivative is an L2 function, it can be expanded in elements of the basis. So there is a natural map, a linear map, taking the derivative of phi n into a linear combination of phi k's. And the matrix of this map is the differentiation matrix of the orthonormal system. And the first result is, which is really a trivial undergraduate exercise, that if all the phi n's obey zero Dirichlet conditions or periodic boundary conditions or Cauchy boundary conditions, then this matrix D is skew-Hermitian. Which sort of makes sense because the differential operator in that case is a skew-Hermitian operator or skew-symmetric operator. And on the other hand, a necessary condition for the existence of phi with skew-Hermitian differentiation matrix D is that the boundary conditions are either Cauchy, so say the whole real line, once we're doing it on the real line, or we have an interval and we have zero Dirichlet boundary conditions, or we have what we call twisted periodic boundary conditions. The value at one end is the same unit modulus multiple of the value at the other end. If kappa here equals 0, there's standard periodicity. Otherwise, we have this sort of twisted periodic, which for a very long time, I believe, has absolutely no applications. And then I discovered that actually it is very important in solid matter physics because it is related to Bloch waves. Okay. Now, remember we have the differentiation matrix, and now I want to impose another condition on the differentiation matrix, which once we are thinking about computations is very natural. I want the differentiation matrix to be tridiagonal, because then it is easy to manipulate it. If you need to solve a linear system with such a matrix, to evaluate the exponential of such a matrix and so on, it is cheap. So in other words, once it is both skew-Hermitian and tridiagonal, we can assume without loss of generality that phi n derivative is of this form here, minus bn minus 1 plus bn, where the bn's are positive. This is not full generality, because full generality is that bn needs to be complex, and minus bn minus 1 has to be the conjugate of bn minus 1. But we can twist, by change of variables, we can bring it to the situation. Cn is also real, and Cn is multiplied by I, and then we have really a skew-Hermitian matrix. And in particular, if the matrix is real, it's skew-symmetric, then we have even simpler expression. And now, and we call such an orthogonal system a T system, T for tridiagonal. And turns out that in each of these cases that I mentioned, Cauchy, zero Dirichlet, or twisted periodic boundary conditions, there exists a T system, and we can characterize all possible T systems. And this has conditions to connections to many interesting facts in analysis. So let us start with Cauchy boundary conditions. We have a whole real line, which in principle is the most complicated case in computation. Because when you think about it, if you have, for example, a differential equation given on the whole real line, doing standard methods like finite differences or finite elements takes an infinite number of degrees of freedom, or you need to truncate the real line, and then you have a different problem. It is complicated. So we are starting from this relation. Phi n derivative is a linear combination of phi n minus 1, phi n, and phi n plus 1. And let us Fourier transform it. Once we Fourier transform it, and we multiply each Fourier transform of phi n by minus I to power n, simply to normalize it, suddenly we obtain something which looks really wonderful. We obtain a three-term recurrence relation. Now, three-term recurrence relation, of course, everybody who studied undergraduate mathematical analysis knows that orthogonal polynomials obey a three-term recurrence relation. Actually, more than this is true. if you have a system of polynomials that obeys a three-term recurrence relation of this form where the bn's are positive, then there exists a Borel measure according to with which they are orthogonal, or orthonormal in this case. So three-term recurrence relation is an equivalent for polynomials, is equivalent to orthogonality for some Borel measure, which by the way need not be unique, but let us not go down that rabbit hole. So, however, polynomials are not the only solution of a three-term recurrence relation. Because take any polynomial solution of a three-term recurrence relation and multiply each Pn by the same function g, what we call a modifier, and then we have a new solution. So the question is what to choose so that we have something sensible. So first of all, let us write a Borel measure as a weight function times d psi. So the weight function is a Radon-Nikodym derivative, so it is in principle a generalized function, but we are not afraid of generalized functions. And take an arbitrary L2 function g. I take non-negative. Actually, we are taking not only non-negative, but I will not go back in that, not go in that direction. And then if Pn's obey a three-term recurrence relation, then G times Pn obey also a three-term recurrence relation. And this will turn out to be a key. And then go all the way back. So G times Pn is a solution of the recurrence relation. This is our minus I to power n times the Fourier transform. Transform it back. You transform it back, we obtain this general formula for phi n's. There is only one problem. Is it orthogonal? There is absolutely no reason that in general, why should this phi n, the system of phi n's be orthonormal? However, it is once you have one particular choice of G. Once you are taking G as the square root of the weight function. Because in that case, orthogonality follows at one from the Parseval theorem. Phi m, phi n is the same as Pm times square root of W times Pn times square root of W. And so it is Pm, Pn, W d psi. This is the Borel measure. We have orthogonality. So this characterizes everything on the real line. However, we still have one problem. Okay, it is orthogonal. Is it complete? In other words, can we take any L2 function and approximate it from this set? And the answer is, there is no earthly reason why. If you are taking our set and you look at the closure of this set, the closure of the set is not L2 of R. It's a Paley-Wiener space. A Paley-Wiener space of all L2 intersection with CR functions, such that the support of the Fourier transform lives in the support of the measure. So if the measure is supported by the interval AB, we obtain only functions which are supported by this, whose Fourier transform is supported by that interval, and later we'll see an example. In other words, what we need is to take a Borel measure that is supported by the entire real line. Once you do it, we obtain completeness. If we don't have completeness, if we have Paley-Wiener spaces, we can still recover completeness by covering the real line by different intervals and taking together several orthogonal systems, each one corresponding to a different interval. And later we'll see one very interesting, very important example of that. So let us see a few examples. One example familiar to everybody in theoretical physics are the Hermite functions. So Hn is the familiar Hermite polynomial. Pn, we want Pn to be orthonormal, so we divide it by the square root of the norm of Hn, and we obtain this function here. And phi n is simply the orthonormalized Hermite polynomial times e to minus x squared over 2. So you're absorbing the weight function into the function itself. And these functions have several beautiful features. First of all, they are symmetric on the real, they are supported on the whole real line. They are symmetric, so the differentiation matrix will be skew-symmetric and real. The Cn's will be 0, Bn's are well known. And the reason why Hermite functions are so important is that they are eigenfunctions of the free Schrödinger operator. So once you are solving any equation which is free Schrödinger operator plus something like linear Schrödinger, nonlinear Schrödinger, Gross-Pitayevsky, and so on, then it makes sense that these functions will be good. Turns out they are not necessarily the best, but they are good. And they can also be generalized in d dimensions using so-called Hagedorn functions or Hagedorn packets. Okay, let us see another example. Let's take Legendre polynomials, normalized to be of norm 1. So now our weight is 1 in the interval minus 1, 1. So the characteristic function of the interval minus 1, 1, and the transform functions are beautiful. They are spherical Bessel functions times the normalizing factor. And they form, it is not a well-known fact, but it is very easy to prove, they form an orthonormal system in L2. But the system is not complete in L2. The system is complete in a Paley linear space because every function that you can obtain as a linear combination of these phi n's, its Fourier transform will live in minus 1, 1. So as far as I'm concerned, these functions are of no interest in computation, but on the other hand, they can be of great interest in signal processing, where one is interested in band-limited functions, but it is not something I understand well, so let's forget it for the time being. And now comes the most interesting example, the Marquis-Takenaka functions. They have been discovered in 1926, in the same year, separately by Marquis and by Takenaka, and then rediscovered by umpteen people, including Norbert Wiener and many others. They are really beautiful functions. And you start from a Laguerre measure, e to minus x at 0 infinity. So the orthonormal polynomials are Laguerre polynomials, but the outcome is not dense in L2. It is dense in Paley Wiener space of 0 infinity. But the remedy is very simple. Add to it the mirror weight, which lives in minus infinity 0, e to x times the characteristic function. Then the functions are, the orthogonal functions, orthonormal functions are ln of minus x. And the functions themselves are really beautiful. They are rational functions, complex valued, because we lost symmetry. So everything will be skew Hermitian rather than skew symmetric. Really beautiful functions, 1 plus 2ix to power n over 1 minus 2ix to power n plus 1. But now n ranges along n is no longer greater or equal to 0. It ranges across all the integers, because n less equal minus 1 are these polynomials, n greater or equal to 0 are this. And Marquis-Takenaka are so wonderful because under this guise, we have here a fast Fourier transform or a discrete Fourier transform. So going back here, look at this 1 plus 2ix divided by 1 minus 2ix. This is a Möbius mapping, and it is of absolute value 1. So it is exponential of I times a real number. And using this as a change of variable, we have, you see, we need to compute coefficients, expansion coefficients, and this is true for any system. We simply need the integral of Fn, phi n from minus infinity to infinity. In this case, because phi n is complex, we need phi n conjugate. And using this change of variable, we obtain a Fourier integral. It is a singular Fourier integral at the endpoints, because at plus minus pi, tan theta over 2 blows up. But, well, no, sort of f anyway goes to 0. This is not the problem. But this weight function, this here blows up. But hopefully, the speed of convergence of f to 0 overwhelms, at infinity, overwhelms this mild singularity. But the important thing is e to minus I and theta. And so we can use fast Fourier transform to compute these coefficients very, very rapidly. And you may ask, are there any other T systems that can be computed using FFT? And the answer is yes, but it is very, very minor generalization of Marquis-Takenaka. You can slightly generalize it, stretch it, twist it, but essentially Marquis-Takenaka is all we can do to compute coefficients with FFT. But FFT is not the only fast transform. There are also fast cosine and fast sine transforms. And also there it is possible to characterize all the T systems on the real line that can be computed in big O of n log n operations. And essentially they can be reduced to functions like this. This is a normalizing constant, which is a large number, but is known. And here we have a Jacobi polynomial, alpha, beta, where alpha and beta greater than -1 of tanh x, and so on. And all these are orthogonal systems. By the way, the underlying orthogonal polynomial is not a Jacobi polynomial. It is a Hahn, a continuous Hahn measure, continuous Hahn polynomial, as it is called. But out of them, when alpha and beta are either +1 or -1, then we have fast transform, either cosine or sine. And in other words, we have exactly 4 T systems for which we have this sort of fast transform. And that's it. And nothing else is possible. It is not an easy theorem to prove, but we proved it. Okay, let me move faster. There is something interesting going on, because there is another way of approaching all that. Give me a function phi naught and tell me that this function phi naught obeys a 3-term recurrence relation. So phi naught derivative is minus bn minus 1 phi n minus 1 plus ICN phi n plus bn phi n plus 1. And start with n equals 0. Then we know what is phi 0. Phi 0 derivative in that case will be I C0 phi 0, which is known, plus B1 plus B0 phi 1. And from this we can find phi 1. Now we have phi 0 and phi 1. looking at the equation for n equal 2, we can find 2 and so on. We can obtain a whole sequence. And turns out that each phi n is a linear combination of the first n plus 1 derivatives counting from 0 of phi 0. And in that case, we obtain a T system, except that the system need not be orthogonal. There's absolutely no reason why it should be orthogonal. So in other words, the problem is overdetermined. If we have the Bn's, we can find unique modulo indeterminate measures phi 0, and then we have phi 0, we can find, and also we have phi n's, and so we can generalize unique orthogonal set. On the other hand, if we have phi 0, we can again generalize a unique orthogonal set, but not for any value of Bn's, but we can generalize the, we can generate the Bn's. We have an algorithm to generalize the Bn's. When you think about it, it is essentially Gram-Schmidt. Because if you know that phi n is a linear combination of the first n plus 1 derivatives, you can use Gram-Schmidt on that to obtain orthogonality. But what is nice, then also it follows that we have this 3-term cancellation for derivatives. Okay, let's move to periodic boundary conditions. Remember, I will not go into twisted periodicity too much for an afternoon, but for periodic boundary conditions, again, it is possible to reduce it to something similar. In that case, phi n can be written as Fourier series, and turns out that coefficients in this Fourier series obey, again, a 3-term recurrence relation. And if essentially, if you have Qn's obeying this sort of recurrence relation, where now the variable ranges over integers, then R and M can be written in this form. And we have a monic system of orthogonal polynomials. But these orthogonal polynomials have an atomic measure. Essentially, the underlying measure has jumps at integer points and 0 otherwise. They is flat otherwise. So phi n is this function here, where we have a measure that jumps wx at integer point x and is 0 otherwise. And for example, Charlier weights. So if we have a greater than 0, and the jump is e to minus a, which is a normalizing number, so that the sum of the weights equals 1, a to x over x factorial, where x are non-negative integers. This is a Charlier weight. Charlier polynomials are known explicitly, and after some algebra, long algebra, we can write phi n's in this form. This lives again not in not in Paley-Wiener space, because it's not the whole real line, but sort of like Paley-Wiener space. In other words, periodic functions in minus pi pi, but whose Fourier transform lives only on non-negative coefficients. But we can again, like we have done earlier with Laguerre, we can add the mirror Charlier with this sort of jumps, and together it forms a complete orthonormal system. 0 Dirichlet boundary conditions. This becomes rather less pleasant. It becomes less pleasant because if phi prime is d times phi, then the L's derivative of phi is d times the L minus first derivative of phi. So if phi is a vector of zeros, all the derivatives, not only the first derivative, but all the derivatives vanish. So if you want zero boundary conditions in an interval, that not only the function, but all its derivatives have to vanish at the endpoints. And given that it cannot be a constant, because then we won't have orthogonality, we obtain functions which are not analytic. And something nasty is happening at the endpoints. And to see why it is nasty and why it is highly, highly unrecommended to use these functions, take the obvious example phi naught, which is normalizing constant, so this of norm 1, times the exponential of -1 over 1 minus x squared, where x lives in -1, 1. So we have essential singularity at the endpoint. We can generalize the T-system, for example, using Gram-Schmidt, and have a look how they look. For 0, 1, 2, okay, but you can already see the problem. The problem is that we are paying for the fact that we have always zeros at the endpoints by having a boundary layer. And functions like this are completely useless in approximation. So zero boundary conditions will not work here. Speed of convergence, very briefly, and also this is an unfinished symphony. So once we have orthogonal polynomials and we approximate analytic functions in a compact interval here is important. For example, -1, 1, everything is understood and understood for more than 100 years. So if f is analytic, not only in -1, 1, but slightly outside, inside the so-called Bernstein ellipse, where rho is a number greater than 1. So this ellipse surrounds -1, 1. Then we have geometric decay of the coefficients of expansion of this function in underlying polynomials, or Fourier expansion, and so on, where Fn behaves like 1 over rho to power n. Remember, rho is greater than 1. The more f is analytic, so in the larger domain it is analytic, the faster it decays, which is wonderful, but doesn't translate to the real line. It doesn't translate to the real line because, first of all, you cannot put a real line inside the ellipse. And most T-systems are themselves singular at infinity. For example, Hermite functions, they have this e2 minus x squared over 2. e2 minus x squared over 2 is singular at infinity, infinity being the north pole of the Riemann sphere. And most functions we wish to approximate, for example, wave packets, are also singular at infinity. Marquis Takenaka is regular at infinity, but in general, the idea of mapping minus infinity, say, to -1, 1 is doomed to failure. And once you map Marquis Takenaka, we have this weak singularity at the endpoint. So again, we cannot use this argument. So now, if we have Marquis Takenaka and we approximate functions which are analytic in a strip, so strip, say, the absolute value of imaginary part being less equal to some positive constant, then they're also analytic at infinity, and then everything flats. And Andre Weidemann proved that if dRu is an open disk of radius r centered at, so it should be u, at a point u in C, then if we define AR and A rho and R rho in this form, then in the closure of this set, take the union of a disk centered at A rho with radius R rho, and remember A is complex conjugate, is pure imaginary, so the complex conjugate simply would be minus A rho, so the reflection of this disk by the real line, take the union, take the whole extended complex plane, take away the union of these two disks, and in what remains, we have, if F is analytic, except for these two sets, then Fn tends to 0, like 1 over rho to power n, which is wonderful. However, it is quite restrictive. In practice, we can do more than that, but let us not go into that. So let me give you an example. F of x equal 1 over 1 plus x squared. This function has two poles at plus minus I. So, and if you surround these two poles by a small, each one by a small disk, it is analytic outside these two poles. And actually, we can write down its expansion in Marquis-Takenaka explicitly, and rho is exactly 3. So we converge like 1 over 3 to the power. Very fast convergence. So here is an example. 2n plus 1 terms goes from minus n to n for n equal 10, 20, 30, and 40. And look, for n equal 40, we already have 20 significant digits. So incredibly fast convergence. Compare this to Hermite functions, the ones that all physicists are happy to use. And the convergence is incredibly slow. In the same setting, after the same number of points, we have an error of 0.0012. So 3 significant digits only, instead of 20 significant digits. And the decay is slightly better than linear. The coefficients decay like 1 over n to power 4 over 3. Very, very slowly. However, so you look at it and say, wonderful, Marquis-Takenaka is a winner. So let us make a small exercise. Replace 1 over 1 plus x squared by sine x over 1 plus x squared. Now, what can go wrong? Sine x is an entire function. Not only it is an entire function, but on the real line, it is always bounded by 1 in absolute value. What can go wrong? So do exactly what we have done with 1 over 1 plus x squared and compute it with Marquis-Takenaka in exactly the same setting. And after 161 points, because 2n plus 1, all we have is accuracy of 0.007, as bad as a myth. What happened? What happened is the essential singularity of sine x at infinity. This kills the speed of convergence. However, what to do? And there is no viable convergence theory, even for orthogonal polynomials on a real line. For example, forget all this. Take plain Hermite polynomials with weight function e2 minus x squared dx at minus infinity, infinity. Take functions which live in the same Hilbert space. Nobody has the faintest idea how fast is the convergence. The completely open problem. Now, there are some problems which are very basic and nobody has the faintest idea.
So, you said nobody knows how fast it's converged. I mean, what topology? The L2 with weight e to minus x?
Yes, with e to minus x squared. Otherwise, Hermite polynomials will blow up.
Even in that topology,
No, nobody has the faintest idea. And when you look carefully at what Bernstein has done and how people extended it and Geronimus and so on, it simply won't work. It's a wide open problem. people didn't look at it. I can tell you stories about it. And I talked with just about everybody of the leading people working on orthogonal polynomials, and nobody had the faintest idea. However, what can be done is steepest descent analysis. Now, steepest descent is a very, very old approach going back to Cauchy and Stokes. People hate it because it is 99% messy algebra, and people prefer not to do it. And also, it gives you something which is weaker than convergence. It gives you convergence in the sense of the Watson lemma. But still, let's try to see what's going on. So Andre Weidemann computed various functions by steepest descent for Marquis Takenaka. So e2 minus x squared converges almost, so like sub-exponentially. There's not e2 minus n, but e2 minus n to power 2 thirds, which is almost exponential. 1 over cosh x is like e2 minus square root of x. Our sine x over 1 plus x squared, the one that was very slow, here, that's why it is very slow. If instead of x squared have x to 4, it is slightly better than quadratic, but that's all. And nobody has an idea what is the general pattern. So really what we have is only this sort of sporadic results. There is one type of functions in which we are really interested, and these functions are wave packets. So functions of this kind, and functions which are wave packets, linear combinations of creatures like that, are very important because once you have a linear Schrödinger equation in a semi-classical regime, where epsilon is small, and this is an equation essentially describing a system of elementary particles under interaction. And epsilon is the ratio, the square root of the ratio of masses of the smallest particles, of electrons, to the mass of the entire system. So it is a small number. Christian Lubich proved that up to square root of epsilon, the solution is a linear combination of, in one dimension, wave packets, in several dimensions, a multivariate generalization thereof. So how well our functions approximating wave packets? Because if you want to use them, for example, in spectral methods for dispersive equations like linear Schrödinger, you want to be able to approximate wave packets well. And the point about wave packets is that this omega here is square root of epsilon. It's 1 over square root of epsilon, which is a large number. They oscillate rapidly. But oscillating rapidly is not a bad thing, as we'll see. And essentially, we have 3 candidates vying for this particular cup. And the simplest one is stretch Fourier expansions. Take Fourier expansion, but in a very long window. Stretch it to an interval minus lambda lambda. Disregard whatever is happening outside this interval, because after all, the wave packet tends to 0 exponentially fast at infinity, and approximate it. And then you have f of t and everything. Amine functions and Marquis Takenaka. Okay, so for stretch Fourier expansions, our basis is made out of such functions, and lambda is a parameter. Now, for this wave packet, turns out that the optimal value of the parameter, remember, omega is 1 over square root of epsilon. Lambda is, no, sorry, epsilon now will be something different. Forget what I said about epsilon. When f is of this form and omega is large, the optimal value of lambda is this, where now the epsilon is the desired error. So if you want to have the solution, say, up to 20 significant digits, epsilon is 10 to minus 20. And the idea is that we need to balance the error we are committing by chopping off everything outside this interval to the Gibbs effect at the endpoints. And this number balances everything perfectly. And it has very, very interesting effect, what we call the Sombrero Effect. So take epsilon equal 10 to minus 20. Suppose alpha equals 1, x0 equals 0, omega equals 50. The exact coefficients are in black. The computed coefficients are in magenta. And look what we obtain. This is the log, to log basis. So this is 10 to minus 20. And see that up to 10 to minus 20, we have perfect fit of what we're approximating to what we want to approximate. Absolutely perfect fit. Exponentially small departure. But little beyond under 10 to minus 20, suddenly we have transition to very, very slow decay like 1 over n. And we know that technically at infinity, it has to be 1 over n. But by choosing our window sufficiently large, we can choose exactly the transition point between perfect fit and exponential, doubly exponential decay and this very, very slow linear decay. And we can place the linear decay in a regime in which we are not interested. We are not interested what happens under 10 minus 20. Or if you really want up to 10 to minus 40, you choose different lambda. Sounds wonderful, but except that there are two problems. The first problem is that we don't know alpha, we don't know x0, we don't know omega, and they change during the computation. And once we undershoot, once we choose lambda too small, we hit the rim of the sombrero too early. Instead of having accuracy of 20 digits, we obtain accuracy only of 5 digits, so 10 digits. If we are choosing it too large, we overshoot. Oh, we obtain too much accuracy, but it happens much, much slower. But what is much worse is that the solution is not a single wave packet. It is a linear combination of an unknown number of wave packets, and these are not solitons. The wave packets change all the time. The number changes. For example, if a particle hits a lattice and undergoes quantum scattering, suddenly out of one wave packet, we can have hundreds of wave packets. And we don't know when it happens. We cannot track them. All this is nice in theory, but of no practical importance. So let us try convergence of Hermite. And so this is an asymptotic formula for Hermite for the case alpha greater than minus a half. And this is only final product. To reach this, you need tens of pages of nasty algebra. And this is really very, very nice, but quite opaque. What does it mean? Well, essentially it means that for a very long time, we have very good approximation. Essentially, and all this again is logarithmic scale, we have exponential convergence for a very long time. And then it will break down, because asymptotic approximation will ultimately break down. But who cares? When we are computing, we are not computing up to, say, 10 to minus 10,000. On the other hand, we don't know whether it will be 10 to minus 10,000, 10 to minus 2. So up to a point, we know what's happening, but only up to a point. And the rate of decay depends on alpha. The louder the alpha, the slower the decay. Marquis Takenaka The analysis is even longer, but the outcome is really, really cool. So essentially, it is possible to prove the following. As long as the absolute value of n is less than a constant times omega, remember omega is a large number, the speed of oscillation, then we have exponential convergence. Provable exponential convergence, exponential decay. So in other words, and this is exactly at the heart of asymptotic expansions. They happen for a very long time, but ultimately they must break down. However, they will break down very much into the future. So for very small values. You know, as long as you want reasonable accuracy, they beat everything in sight. And the absolutely amazing fact, which is completely counterintuitive, unless like me, you work for the last 15 years on highly oscillatory phenomena, and then this comes as something very natural, the faster the oscillation, the better it is. Because the larger omega, the larger the domain of exponential convergence. Then if omega equals 0, we have sub-exponential convergence. Then we are in the scenario that Andre Weidemann proved. We have convergence which is sub-exponential, e to minus mod n to 2/3. But once omega grows, once we have fast oscillation, we have longer and longer interval of exponential decay. And the bound is really perfect. So exact coefficients in green, our estimate, it is supposedly an estimate, but it's really a perfect estimate. It's exponentially, doubly exponentially true estimate in black. And you can see it is virtually perfect. And the larger omega, no, all this is for omega equal to 100. The larger alpha, the thinner it is, but I didn't go into that. And overall, Marquis Takenaka wins this particular competition. So this is not the entire story, but this is as much as one can do in a lecture. So I suppose I should stop now. Yes, there is a bibliography, long bibliography, but I will not go into that. Okay, thank you.
So questions either from the live speaker or the live audience or virtual audience.
What if you're doing a Schrödinger equation where you've got a dissipative barrier? What if you've got a dissipative barrier in your Schrödinger equation? Does this have any effect at all?
Well, as long as you have a Schrödinger equation, the dispersive equation preserves mass. So you will not have dissipation.
It doesn't preserve mass.
No.
Okay.
No. If you have dissipative equations like, say, parabolic equations, then, you know, dissipativity forgives many sins. As always, I tell my students, parabolic equations are Catholic, hyperbolic equations are Calvinist. Every sin is written down and you'll have to answer for it.
And the other question I was interested in is, what is Malmquist Takenaka bad for? I mean, you've shown us what it's good for. If you wanted to break it, for sure you know how to break it. How do you break it?
Well, how to break Malmquist Takenaka? So one possible way of breaking it, So I had a discussion about it with with my friend Nick Trefetten, and Nick says that he dislikes Marquis-Takenaka because they are too much centered about the origin. They privilege the origin too much. Well, this is also true for Hermite and other functions. We didn't observe this behavior, but possibly something might happen. One point about Marquis-Takenaka, okay, this is Marquis-Takenaka decay quite slowly. They have a very fat tail. Essentially, they behave like a constant divided by n at infinity, or like constant divided by 1 over x, or constant divided by x for very large mod x. And this means, for example, that you cannot use them for functions that themselves decay very, very slowly. Actually, again, it is a conjecture. So, for example, we are taking like 1 over x will not be L2. No, 1 over x will be L2. Say 1 over 1 plus x squared. No, 1 over 1 plus x. Now, the problem is that
1 over 1 plus the square root of mod x.
1 over, well, mod, okay, exactly. 1 over 1 plus mod x will not be analytic. 1 over 1 plus x will have a singularity at -1. 1 over 1 plus x squared, we know everything, and it converges exponentially fast. But 1 over x squared goes down fast to 0. We don't know. The problem is people have used Marquis-Takenaka quite heavily in various areas, John Boyd and others, also in computations, but somehow there is very little theory.
Further questions?
Yeah, I have a question.
Sure.
Maybe it's a slightly strange question, but I was wondering if it's orthonormal system Marquis-Takenaka, can they be expressed as perhaps the eigenfunctions of a linear operator, something like this?
Well, Hermite functions are eigenfunctions of linear Schrodinger operator, of free Schrodinger operator. I'm not aware of any other results of this kind. And even when it comes to Hermite functions, okay, so there are eigenfunctions of free Schrodinger operator. So what? That's nice. That's one of the reasons why physicists love them. But is it somehow helpful in computation? It is, but it would have taken me another hour to explain the mechanics of why, and it is unrelated to this.
So if there are no further questions, doesn't look like there are any from the virtual audience. Let's thank the speaker again for the very interesting talk.